Okay, so now I'd like to do one more case of integrating secant to a power times tangent to a power. So we just covered the case where the exponent for secant was any even integer. Now as it turns out, as long as the exponent for tangent is odd, and n is at least 1, I need some secant there, I've got a procedure that's going to work, and it's really very, very similar to what we did on the last one with secant to an even power, and also the sine and cosine integrals. We're going to use these identities, which allow us to rewrite secant to an even in terms of tangent, and tangent to an even in terms of secant. So let me just do a quick example to illustrate the procedure before I give you the general procedure. So let's make it as simple as we can. I'll just have one copy of secant here, and then let's say I need tangent, power of tangent to be odd. How about tangent to the third x dx? So when we, on the last case where we're doing secant to an even power, we ended up letting u equal tangent, and we needed a copy of secant squared by itself for cancellation. Well, this one is going to be the other case where we let u equal secant. Now, as the derivative of secant is secant tangent, I need a copy of secant tangent off to the side for cancellation. So, in order to get that, we're going to pick one of these tangents off from the 3 that we have here. And what that does, since we started with an odd power of tangent, now we have an even power of tangent. How does that help? Well, even powers of tangent can be rewritten in terms of secant. So I can rewrite this in terms of secant. And then I have the derivative of secant sitting all by itself for cancellation. So let's go ahead and do this. Secant squared minus 1. Now you let u equal secant x, etc. So what do we get here? Secant x tangent x. That's going to be u squared minus 1. Dx is going to be 1 over secant x tangent x du. And you see that we get it entirely in terms of u now. So the antiderivative of u squared minus 1, that's 1/3 u cubed minus u, 1/3 secant cubed x minus secant x plus c. Okay, so that's if we have tangent just to the third power. And as I mentioned earlier, the same modification of this procedure anyway should work if I have any odd power of tangent and any power of secant. So to prove my point, I'm going to make the exponent for secant some ridiculously large number. How about 100 this time? And now I just need the power of tangent to be odd. Let's make it a little bigger than 3. How about 5 this time? Now you should keep in mind that our ultimate goal is to let u equal secant. That said, I need a copy of secant times tangent just sitting all by itself, so it will cancel out when we get to the u sub. So if I do that, I get secant x tangent x. Now I'm going to have tangent to an even power that can be rewritten. It's going to be even because I started with odd, and I always pick one copy of tangent off to form the secant times tangent over here. And now I'll have one fewer copy of secant, which isn't going to be important in the end of things. Rewrite. And save for cancellation. Okay. Secant x tangent x. That's tangent squared, quantity squared. Tangent squared is secant squared minus 1. So secant to 9 here. And now, if I let u equal secant, all of this will be completely in terms of u. It will be a polynomial. I multiply it out just like we've done on all the previous examples and integrate one term at a time. So if I let u equal secant, and I'll leave the details of the u sub for you. The secant tangent's going to go away. I'll end up with u squared minus 1 quantity squared times u to the 99 du. So we're going to multiply this out, then distribute the u to the 99 across. U to the fourth minus 2u squared plus 1, u to the 99 du. Now, nothing special about that 99. I just got to add that to all of my exponents. That's u to the 103 minus 2u to the 101 plus u to the 99 du. One term at a time, 1 over 104. What was u in this case? Secant. Secant to the 104x minus 2 over 103, 101 plus 1 is 102. Secant to the 102, and then plus 1 over 100, secant to the 100. And we're done.